Good. Welcome, Biochem 2. So we've got lots to do in this class, and kind of gets kind of a big class in a junior level, but we have two people feeding in, or two different paths. Well, some of you have been just in cell biology, and some of you have been Biochem 1, but we all meet together in Biochem 2, and then you split apart into two different classes again next semester, but by chance all of you will be sitting in the same room. And so the Biochem 3 and the molecular biology, actually the same class. We just have you in two different classrooms. They actually sit in the same class, and Dr. West and I teach that class together. And so we'll be together for a little while, most of you. Right. Metabolism overview. Okay. The key to this is knowing that what we're really doing is converting things around. Now, if I say metabolism, what does that make you think about? You've heard the word, right? Yeah, breaking down food into energy. Anything else, though?
How you keep and maintain weight.
Yes. Yeah, how you maintain weight. And actually, there is a lot of balance in trying to keep everything running correctly. There is one more aspect of it that actually we don't deal with a lot. We'll deal with a little bit, but actually goes into the next semester. We not only degrade, but we also synthesize. And so we are going to interconvert all of the material that we take in, usually through eating, and make all the different molecules that we see in the body. Some of which we can actually synthesize. Some of which we have to eat in its entirety so that it can be functional inside our bodies. And so metabolism are these reactions. Now, a lot of times when we look at it, metabolism is really a way to organize all of these pathways in which molecules are interconverted, and we display it in a picture sort of like this. It's almost like a map, okay? And the map can go lots of places. And so if you look at metabolism, you get lots and lots of arrows. Those represent series of reactions, and in almost all cases, almost all of these different molecules can be interconverted amongst themselves. Okay, and we do that in a lot of ways within the system. Now, this particular picture kind of incorporates both plants and animals, so not all of the pathways are available in every system. There are some pathways that are only one way, but most pathways are two ways. And what we're going to do is we're going to learn each pathway independent of each other, all right? But then we're going to integrate it at some point in time. And so glycolysis starts up as glucose and goes to pyruvate. Those are two molecules at the beginning and the end, the alpha and the omega. But when you actually get to pyruvate, okay, you can go lots of different directions. Now, we'll teach you one direction and then go off on that. But later we'll come back to pyruvate and go into a different direction, and then we'll go into a different direction. And so, like a map, we're going to be able to, as we learn more, go different places and go in different ways, all to get to the same place. And so, what we are going to learn behind that is the regulatory events that make it shift one direction or the other, and kind of think about how it all works together. All right? Now, most of the time what we're learning is this. We're learning the way it is supposed to work. Okay? That's where we get to when you're going to apply. Usually we look at this when it doesn't work. And so you have to know how it is supposed to work so that when some sort of error is introduced, you can actually determine where in the process the problem was. And so if you know the forward reactions, the backwards reactions, if you know what forwards and backwards, then you'll be okay. All right? And so everything forwards and backwards. All right, we're going to review just a couple ideas. Oh man, delta G. We're going back to G-Chem 2. I know that's a scary thing for most of you. All right, what is delta G? Free energy, okay? And what is important about the sign in front of the number? Change. Yeah, it's a change in energy. So if it's negative, or if it's positive, or it's zero, what do those mean? So let's go, what if it is negative? Spontaneous. Okay, what does that mean? Are they free, fun-loving, spontaneous? What does that mean? It should go in the forward direction. Okay? That means the reactants are more stable than the products. And we want to proceed towards, the products are more stable than the reactants. It wants to go towards the product. Okay? The higher the negative value, the more likely it's going to move. All right? What if it is positive? The numerical value. It's exactly the opposite of that. It would rather be the reactants rather than the products. Okay? What if it's zero? It's in equilibrium. That's exactly it. That means they are interconverting, and there will be a distribution between the two. All right? And so we can represent that in a chemical formula with arrows, single arrows one direction, or reverse arrows in an equilibrium. And so that's important. Now, this slide shows negative values and only. And I show you in kilojoules per mole and kcals per mole. Most modern texts use kilojoules, although kcals are used quite often in older texts. And when you look at this, there's a whole list. Which one is kind of the defining one? Do you know? Which one is the one that we kind of relate everything to? Yes. And PI, yes. So this is the defining reaction because we use ATP to power almost all things within the biological system, the most often used. Negative 30.5 kilojoules per mole, or negative 7.3 kcals per mole. Okay, it's a very energetic molecule. Is it the most energetic molecule? Obviously not. Why in the world do we even have reactions that are more energetic than ATP if we use ATP all the time? Many times what's going to happen is the ones that are more energetic are the very few reactions that are able to create ATP. And so there are a few reactions that can occur that actually can make ATP back from ADP, the diphosphate, and an inorganic phosphate. But most everything else, if I use ATP, I can make the reaction go forward or overcome a positive delta G and actually allow the reaction to proceed. Now, what is this problem? If you went back to GChem 1, what would this type of problem be called? What? Hess's law. Yeah, I got it. I remember something from general chemistry. Okay? And remember Hess's law, we did a little bit differently. What you did was you had to make sure that the reactions were such that when you canceled everything out, you got to what was at the end. And so if phosphate's on one side and phosphate's on the other, I take that away. And if I have water on one side and water on the other, I take that away. And then I drop down everything that is left over. That's the reaction. And I would add up the energies, and then you find the energy of the overall process. But what if you had to switch the reaction? What if I actually had to flip the reaction so that it crossed out? What would you have to do? You have to change the sign on the energy. So that's important because quite often on a standardized test, they will have the reactions in which you would have had to switch one of those. Okay? And in GChem, we did all kinds of sorts of things in which you only used a half of a reaction, so you only used half of the energy, and we did really weird things like that. But in essence, to react glucose and put a phosphate onto it to make glucose with a phosphate in the 6th position, Okay? That doesn't like to happen. But if I take ATP and break it down, I have enough energy to cause that to move and to proceed, and it would proceed pretty well. Okay? Now, in GChem, we just think about those things happening separately. Okay? But what's going to happen is it happens in a stepwise fashion, how we transfer energies in intermediate steps to actually make this reaction go forward. But we are applying Hess's law. Now, the energies that I had on that chart are delta G prime naught. Okay, what in the world is all of that? All right, standard free energy, the prime means things like it's all at 1 molar concentrations of the reactants and the products. It is at 25 degrees. It's at 1 atmosphere. These are the standard set of guidelines when we calculate these things. The naught has a couple extra things because we're in biochemistry, and that is a pH of 7, because pH influences a lot of biological systems. It also has 1 millimolar of magnesium, which is kind of oddball, okay, and it comes across once, and then you have to know it for the rest of your life. Anytime you have phosphates running around in the system like ADP or ATP, magnesium is always there. And so, anytime you see phosphates or nucleotides, you have to have magnesium there. It's the only time we tell you. Now we assume you know forever and ever and ever. Okay? And we also have a concentration of water at 55 molar. Those are the concentrations and parameters for that extra value in the biochemical free energy. All right? Now, if you think about it, I don't think there is one reaction in the body that has 1 molar concentrations of anything, okay? So those standard numbers, those values, really don't represent what's actually happening. We actually have to take into account the actual concentrations of each of those, and depending upon the reaction, you have to take into account the coefficient and the concentrations to actually calculate it. And then you go back to GChem 2, really, and you see that the real delta G is the standard plus RT natural log of the products over the reactants, and you would have to put the coefficients on there also. Okay, here's what essentially are the important parts. This could be positive, okay? But we can manipulate the system. If by chance this concentration, okay, right here, compared to this concentration, if that fraction is less than 1, when you do the RT natural log, you can get a negative number. And that negative number can actually drive the reaction. So how do I get a negative number? Big, small. If by chance I manipulate the system and I give it a whole bunch of reactant and almost no product, you can force it by mass action towards product if you have a large enough difference. The body will use this strategy. The reason is what will happen is every product that is formed almost all the time will then be used in another reaction. So the product is always being drained away, so the reactant stays very high and it pushes it through. And this is one of the reasons why we can go to completion 100%, is by using this particular principle. Now, the real energies for ATP are manipulated in 2 ways. One, the concentrations, what's really happening inside the cell, because they're not all 1 molar. And secondly, magnesium. Of the 2, the concentrations or magnesium, which one will always lower the energy of ATP? Talk amongst your neighbors. Okay, so of the 2, the concentrations, okay, the different concentrations could be plugged into that equation, and it could take away the energy from ATP, okay? Could add to the energy of ATP depending upon the different concentrations. The magnesium could take away potential energy of ATP, or it could add, okay? One of them will only take away the potential energy of ATP, how much energy you can derive, okay? Is it the magnesium or is it the concentrations that take away how much energy you can extract from ATP? Okay, what do you need to know first to even answer that question? Why does ATP have energy? Because of the phosphates. What about the phosphates? They're negative. And what's bad about the negative? Or they're all very close together. What do we know about negative charges? They repel. But if you put them close together, they repel. Yeah, they're really not happy, right? And so, but they're being held by covalent bonds, so they can't get away, right? But if you break it, what do? You separate the charge, right? That's one of the aspects. The other aspect, once the phosphate falls off, you get more resonance structures, and that's always more energetically favorable. Okay, so that's how ATP gets energy. So which two of these entities could or always takes away energy from ATP? Magnesium. Okay, good. 50-50 chance, got it right. Now, why? Yes, it's a charge thing that it binds to the oxygen's negative charges, right? And it makes an interaction between that magnesium that has two positive and those negatives. And so what it does is it hides a little bit of those negatives away from each other. Well, that's where the energy was. And so magnesium always lowers or stabilizes the ATP. All right? Depending upon the concentrations, you can actually either add or take away the amount of energy, all right? And so if you actually do calculations, you get a larger number, a very much larger number of energy in kilojoules per mole for breaking ATP, even with the magnesium there, okay, if you use real concentrations. Unfortunately, though, all the other reactions that you have in the body aren't at 1 molar either, and so they cost more energy. And so even though you get more energy, every reaction that you have to power costs more energy. And so what actually happens is, almost all the time, if you do calculations just with the standards, the shift is almost the same for both entities, so you're always taking in a difference. And so if you estimate with just the standard energies, it doesn't actually tell you what's really happening in the cell, but it gives you almost always the same outcome. And so we can use the standard energies to make good estimations. Every so often, adding two standard energies together doesn't actually represent, but you know, if you could go into a test and get it right 98.5% of the time without studying, would you be okay with that? Every single quiz, exam, and everything? Yeah, about 90% of people in this class would say yes, but I could do better. All right, I know you guys. But here we go. If you take a look at the phosphate bond itself, there are a couple of reactions that are called high energy compounds or low energy compounds using ATP as the standard. And so one textbook separates the reactions that way, but there are just a handful of reactions that actually give off more energy than ATP. Almost every other reaction can be powered just by ATP alone. All right. Now, if I actually take a look at the high energy reactions, there are 1, 2, 3 reactions on the board, all right, on the screen. All right, what is the guiding principle that allows the reaction to give off so much energy? All right, again, talk to your neighbor. What is common, the common theme between these 3 reactions? All right, anybody want to volunteer your group's answer? I know it's going to be your partner's answer, so it's not yours, so you don't have to be afraid. Yes. Okay, they're all hydrolysis, okay? And so if you compare these reactions to ATP, they are both hydrolysis. So that is not why we get so much energy. But it is common. In both ATP and each one of these reactions, we do remove a phosphate. But that's not the answer. That is common, but that isn't why we get so much energy. Resonance. Okay, here, the hydrolysis of the phosphate. When phosphate comes off, you gain more resonance structures, and that is better. But when you break off phosphate off an ATP and you break off phosphate of each one of these, that is very similar. Both of them resonate as many resonance forms as possible. Okay? The ATP, the ADP is locked in its resonance, the possible resonance structures. Okay? So one half got to resonate, and the ADP was a little bit locked. But in each one of these reactions here, not only does the phosphate resonate, but the final product also has resonance structures. Now, do you remember when you had to draw all the resonance structures of, that kind of problem? It is important because if you are able to draw resonance structures, it brings a lot of stability. It is a driving force for why reactions can occur. Okay? The more that you can draw a resonance structure, and it's one of the principles that stabilize organic reactions, and it's one of the principles that is leveraged within biochemical reactions, is to create resonance structures to create a stable intermediate or a stable structure in the process. So it's that additional resonance stability. All right. ATP has lots of phosphates. They have lots of negative charges. They don't like to be around there. Okay? And you could attack the phosphate at three sites, the electrophilic sites, where a nucleophile can attack. You can attack at either the alpha, the beta, or the gamma phosphate. Alpha being the one closest to the sugar ring, the ribose ring, and gamma being the farthest away. Now, a lot of times you're not going to be shown the organic mechanism in the textbook, but what you can do is extract back by looking at what is produced. Okay, and so here I have a nucleophile, an R group that has a negative oxygen. All right, if it attacks at the phosphate of the alpha right here, okay, remember electrons always attack in organic reactions, and so it's going to attack this phosphate. The phosphate has a double bond. Okay, anytime that you attack something with a double bond, the mechanistic steps is you draw a electron pair that goes up onto the oxygen itself. Okay, in this case, the what would be the transition state would be a pentocovalent intermediate, 5 things bound to it. Then it will kick down to reform the double bond, and then I will break the bond. This bond, the electrons go onto that oxygen. All right, I will add 1 phosphate plus ribose and adenine, which is called AMP, and 2 phosphates fall off. Okay? And so if you see at the beginning ATP, and you see at the end PPI fall off and an AMP stuck onto your molecule, it attacked at the alpha. If by chance, though, the nucleophile attacks at the gamma, you'll see the electrons kick up, you'll see the electrons kick back down, and you'll see this bond broken where the electrons go onto that oxygen. And what you have is a leaving group of adenine, ribose, and diphosphate, ADP, and your molecule will have 1 phosphate added on. Okay? In the beta, AMP falls off, and you've got 2 phosphates attached. All right? Most often, yes.
So could it not
Yes.
Could it go the other way?
Potentially, yes, but the enzymes that facilitate the reaction only allow it to go one direction. And so it only goes, we only see this version of leaving groups. Okay? 2, so we transfer most often the gamma phosphate. Then you will see a few transfer an AMP. Very rarely will you ever see this. Okay? Now, why in the world would I attack either alpha, beta, or gamma? Okay? Unfortunately, it sounds like a cop-out, but it really is true. It is the enzyme that orients the two reactants for where the reaction is going to occur. And so if I'm going to attack the gamma, it places the reactant right next to the gamma phosphate so that it is one bond length away. And that's the one it's going to react to. Or if it reacts with the alpha, it will bind the ATP in such a way that the reactant is right next to the alpha phosphate. And so the enzyme directs where it goes and why it will stabilize that transition state to allow the reaction to occur. Okay? And so knowing where it attacks alpha, beta, or gamma, looking at the outcome is an important thing for you to know. Important when? When does it become very important? On the test, that is correct. Okay? All right. Now I told you ATP can be used to power reactions. This is Hess's law in an organic reaction without any numbers. Okay? No math. I like that better, right? And so this is the application of Hess's law. All right? And this reaction actually has a molecule called glutamate. Classify that molecule for me. What kind of molecule is glutamate? An amino acid. How many amino acids are there? 20? Is that all the amino acids that you know? There are 20 amino acids that are incorporated into proteins. There are thousands of amino acids, a lot of them not incorporated into proteins, but we talk about 20 most of the time. And you need to know the structures of those 20s and the names of those 20 amino acids, so that's important. So that's one of the reactants. We have ammonia and we have ATP. 3 reactants. Very rarely do we have ever 3 things reacting at any one time. Usually we do 2 things at a time. And so having 3 reactants usually means you have 2 reactions that are occurring. But this is a common theme. I'm going to add this to that, the ammonia to this molecule. In the process, I'm going to break ATP down. Okay? I'm going to use the power of the ATP to cause this to go here. Okay? And you see this a lot of times. What really happens is a reaction between the glutamate first and the ATP. Now, looking at the ATP in the product, I will mechanistically attack the phosphate on the alpha, the beta, or the gamma. The gamma. Okay? The nucleophile that will attack is this negative oxygen on the glutamate. How do I know that? Look, that oxygen has a phosphate attached to it. Okay? And so what would happen is I would go and attack the ATP, and if I drew out all of ATP, I would hit the gamma, the furthest one away. Electrons kick up, electrons kick down, and I get an intermediate molecule. Inside the enzyme, this never leaves. So you never find it floating around in the body, but it's part of the transition of this sequence. Now, what I'm doing is I'm actually investing energy, okay? Because that's why I needed ATP, right? And I put a phosphate right here, okay? Now, how in the world does putting a phosphate right there invest energy? What we are actually doing, we are taking the molecule, the glutamate, and another terminology we can use, we are activating the glutamate, all right? But why does this phosphate activate the glutamate? Do you know? Okay, let's look and do some inventory. There is a nitrogen here, right? Here is a phosphate. Okay, that's different, right? The nitrogen is attached to what? The carbon of the carbonyl, right? And so that's this thing right there. All right, if I had this attached there, then that has to fall off. This becomes a what kind of group? What do we call that? A leaving group. A phosphate is a much better leaving group than would have been a hydroxide leaving, which would have been what would have left if I just attacked the glutamate directly. That's really high in energy, a hydroxide falling off. But if I put a phosphate on it and I attack, then a phosphate leaves. I can make lots of resonance structures, and it is much, much more reasonable for it to, and less energy for it to react. So if I actually took the nitrogen of the ammonia and I took a base inside the reaction, I can take that proton. The pair of electrons here now go on to the nitrogen as a negative charge. A negative electrophile is a wonderful attacking group, and it will attack the carbon of a carbonyl. Why would a nucleophile attack a carbon of a carbonyl? It happens all the time, but why? The oxygen pulls the electrons. What is the principle of the oxygens pulling the electrons called? Electronegativity. The oxygen is much more electronegative, pulls the electrons away, making the oxygen a little bit partially negative, which makes the carbon what? Partially positive. That negative nucleophile loves to attack that positive charge. Every time I react with something that has a pi bond, the transition is up. If I had 3 things attached to it, the transition state is a tetrahedral. 4 things attached to it, that's the transition state. It's excited, it will fall back down, and what will happen is it will have the phosphate leave, and I end up with the product at the end. Now, a lot of reactions will allow one phosphate to be transferred to become a good leaving group and then a secondary attack. This is how I invest the energy of the ATP into the molecule for a little short period of time and then allow that energy to be released when I wanted to finish out the reaction. Okay, this is Hess's law, actually stepwise. Connects together, transfers the energy from one to the other. ATP, if you do by chance attack at the, and this is an example of attack at the alpha carbon, okay, what you do is you have a PPI leaving group, okay, 2 phosphates attached to another. There is a ubiquitous enzyme called inorganic pyrophosphatase. Okay, I just used a word. Do you know what that word means? Ubiquitous, yes. Everywhere, yes. Scientists love to use words that nobody knows, okay? So this enzyme's everywhere. Anytime 2 phosphates come off, they're immediately broken down into individual phosphates. The 2 phosphates had negative charges next to each other. I broke them apart. I actually extract more energy from the reaction because I extract energy here. And this is a wonderful leaving group. I'm going to attack something right at the carbonyl, and it's going to fall off, and that's a great leaving group. And so I have actually invested lots of energy to fund this particular reaction. I actually get a little bit more bang for my buck out of ATP, but at the end I have AMP. So what the body has to do is it has to phosphorylate it up to ADP and then phosphorylate that back up to ATP. And so it takes me more energy to get it back to its starting spot, but I can use 1 ATP and extract lots of energy from it. Sometimes we will do that, and that's where you see the alpha attack more often. All right. Before we go on to glycolysis itself, we need to talk a little bit about sugars. And so sugars are organic compounds that have at least a carbonyl, okay, and at least 2 hydroxides that are contained there. Now, these have a little bit more hydroxides. 2 sugars, glucose and fructose. All right. Has anybody ever eaten glucose? Have you? Where do you get glucose? Plants and sugar? Yes, there are some packets like that. Most of the time, if you actually ingest glucose, it's in a bag, in an IV, and they call it dextrose. Glucose is not really eaten too often. We talk about it all the time. What is the sugar that we eat all the time or we put in our coffees? And it's called sucrose. Okay? It does have a unit of glucose in it, but it's not glucose by itself. Okay? Fructose, where do you eat that from? High fructose corn syrup, yes. It's also it's the natural sugar in like fruits. Okay? And so you can actually ingest fructose itself a lot more often than you can ingest glucose, but we almost always exclusively talk about glucose. All right? Glucose can be drawn in different ways, and we use a 6-membered ring for glucose most of the time, but this is absolutely, this drawing, fictitious. Doesn't look like that. Okay? It looks like this. Okay? Remember these things? Boats and chairs? Can you draw them? Not very well. Okay? But this actually represents what it physically is shaped. Okay? So that's what is really there, but we use these kind of drawings to tell you some things and to be able to see things a little bit easier. Why is it take this form? Why does it have either a boat or chair? Sterics. And remember, if you have a carbon that has 4 things attached to it, it has to be in tetrahedral, and that either the chair or the boat allows a tetrahedral shape. Okay? All right. Now, when you look at sugars, there's a little bit more stereochemistry involved. Not just can they be called R and S, they actually are defined as D and L. And what is that? When you draw the structure, we use a particular drawing method in which we place at the top whatever the ketone is, whether it's an aldehyde or a ketone. It's at the top. Then we identify all of the hydroxides that are there, and we have a hydroxide at the end. Okay? The last hydroxide that has stereochemistry, which is this one. All right? This is where we get either the D version or the L version. If drawn in this particular method, if it is on the right, it is called D, and if it's on the left, it is called L. Now, D and L doesn't have to be, D is not like S or R and L is the other. You can actually have D and L and it has no necessarily reference to R and S, but we use this particular naming system for sugars. The reason why glyceraldehyde is used, it's the simplest sugar, a ketone with 2 hydroxides, and you have to have 2 or more. With simple sugars, that ketone or that aldehyde can be attacked by alcohols. All right, and if you do, you create 2 structures, one called hemiacetal and hemiketal from the aldehyde or the ketone. And this is how we're going to attach sugars in long polymers. So this reaction is reversible. Because the hydroxide that is formed can be deprotonated, reform the ketone, and the alcohol can fall off. So this is a reversible reaction, but this is how we hold sugars together. When we look at a sugar like glucose and we get it in a jar and we put it into water, the sugar distributes between three forms, okay? The acyclic form, a straight chain, and cyclic forms. Now, depending upon how the attack occurs, the hydroxide, which is an internal attack, so this D hydroxide will attack the carbonyl to create a ring structure, and you can get either an alpha, meaning this hydroxide's below the ring, or a beta, the hydroxide's above the ring. The reason why we draw this particular structure is to show above or below the ring very easily. That's why we draw that one. And so the alpha or the beta form can be formed, and the relationship between alpha and beta are called anomers because this carbon is the anomeric carbon, and it can become the alpha or the beta. The most stable form of glucose is D-beta, and I'll show you why in a moment. There is one more other type of drawing that you can see. This was actually done when people were using typewriters still. This was much easier to draw before drawing programs and computers than something like this. And so you'll see in very old journals a lot of drawings like this, because that is one long bond right there, you know? But it represents this bond right here. That long thing represents that bond or this bond, all right? And it's just, you might see that Fisher projection every so often. The Fisher projection will actually allow you to see this is the D, because it's on the right side, and an L would be on the opposite. The reason why the glucose is beta D is because of this. Here's a hydroxide, there's a hydroxide, there's a hydroxide, there's a hydroxide, there's a hydroxide. The hydroxides in a beta D form are all on which bond? These two are categorized as two different things. Either, and here's a hint, it's either A or E. Equatorial. And if they're all on the equatorial, the largest things are on the equatorial, there is less steric interactions. If there is one structure that you probably should be able to draw after we look at metabolism, okay, actually draw. Because the body is very, very sensitive to this particular molecule. Okay. We have two forms of rings, 5-membered rings or 6-membered rings. We name them furanos or puranos based upon the organic solvents, pyran or furan, because they are 5 or 6-membered rings that include an oxygen in the ring. And so they're just connected because they look like them, and that's why they derive the name that way. We talked about the glycidic bonds as being how we actually bond sugars together, and it leads us into this, the disaccharides. These are sugars that you eat quite often. Up at the top, you have lactose. In the middle, you have sucrose, and at the bottom, you have tetralose. Where do you get lactose? Milk. Where do you get sucrose? Sugar cane a lot of times, and or beets. You get that good pure sugar. And then tetralose is the degradation of starch. Okay, so these are ones that you interact with quite often. All right, you need to know these. Now, what do you need to know about them? Which two sugars are connected? That's important. And secondly, what is the connection point? Okay. And so what we're going to do is galactose is a beta 1,4 bond. All right. The sucrose is an alpha 1,2 bond between the glucose and the fructose, and the tetralose is an alpha 1,4 bond between the two glucoses. Okay. And so which two sugars are together and what the bonding is between them. So lactose, sucrose, and tetralose. Now what's interesting about this is we eat lots of disaccharides, okay, but we can't absorb any of them. We can't actually get them into our bloodstream. The intestines will only allow single sugars to come through the intestinal wall. So if we eat any of these, we then need an enzyme to break down those. Now, in naming of enzymes, if you put ACE at the end, it creates an enzyme, and the most simple enzyme is one that breaks something. And so to break lactose, you use the enzyme lactase. If you have sucrose, you need the enzyme sucrase, tetralose, tetralase. Okay? And so if you take a look at all of those, we have those enzymes, and that's great. All right. What if you don't have one of those enzymes? What? You won't be broken down. Is that good or bad? Bad? Why do you say bad? You just put it out your waste, right? It won't be absorbed. You just eliminate it, right? And all is happy, right? No. Okay. Have you ever heard of lactose intolerance? So your lactose intolerant friend goes to the Baskin Robbins with you. Okay? You enjoy your time. They don't. Okay? What happens is they eat lactose. Okay? That's fine. Eat it. Goes to the stomach. That's fine. Gets to the intestine. They don't have a functional lactase. Okay? So what happens is they break down all the other sugars, but not lactose. Now here is a problem when you have lactose in your intestine and not in the bloodstream. The intestinal wall is a semi-permeable membrane. Have you heard that? Semi-permeable? Okay. That means things can move back and forth, usually water. Okay. Now here's the principle about a semi-permeable membrane. If you have something really concentrated on one side and really dilute on the other, the principle is the semi-permeable membrane tries to dilute one side of it until the concentrations are equal. So you've got lots of lactose in your gut and none in your blood, and so what happens is you get a flood of water in. You're gonna eliminate it, but it's gonna be lots of watery. Also, you get cramping, and so it just doesn't feel good. All right, and so the lack of this enzyme, either in the case of it was never produced in your body, or traditionally in a lot of American diets, the lactase tends to lose its activity as you grow older for a lot of Americans. And so you can get to the point that you become lactose intolerant. What's a solution? What's a treatment? What? Don't eat lactose. That is absolutely a treatment. No ice cream, no milk, no cheese. That is not a life I would like to live, okay? So what other treatment could you give them? What is it? A lactate pill, okay? Lactate is basically lactase, and you eat the lactose and you eat the enzyme all at the same time. And you allow that to go through, and you digest it as you go through. Or you can buy milk products that have been treated with lactase, and so it has everything in there, but what they did was took all the lactose and broke it into individual glucose and individual fructose, and you can take that and ingest it. And so there are mechanisms at which we can treat the lack of an enzyme here and be functional. I wish we could do that for every disease, but we can't. Okay? Now, when you do hydrolysis of starch, okay, a more formal name of starch is amylose. It's actually started by amylase, the alpha amylase, and this is actually the first part of digestion. And it's an experiment that elementary school kids do sometimes. And if you take a saltine cracker, okay, and you take a bite and you start to chew it. Now, most of us, when we're eating a saltine cracker, it goes down very, very quickly. But if you ask the elementary school kid to take it and just keep chewing and keep chewing and keep chewing, okay, that's odd, but it allows time for the amylase in your mouth to start working on the starch, and over time, it actually starts to taste sweet, because it actually gets down to breaking it down to small enough saccharides that actually bind to your receptors, your sweet receptors. And it goes from a very relatively bland, unless you have salt on it, a bland starch into something that is sweet. And you can actually detect it with your own body, the actual progression of that reaction. All right, and it's one of the first digestive enzymes. Now, eventually, we eat lots of things so that we can get down to one of the energy sources called glucose. And so what we're going to do is we're going to break down glucose oxidatively to extract a little bit of energy. Okay? Look at that number. That is huge, right? Look, if you look back at the other chart, we were talking 30. Right? This is 2,840 kilojoules per mole. Okay? Now, a mole of sugar is like 500 grams. All right? So if you ate 500 grams of sugar, okay, which is about a pound, okay, that's 2,840 kilojoules of energy. Or, think about it another way. If you want to lose a pound of sugar, you have to work out and burn 2,840 kilojoules of energy to get rid of that. Okay? Now, we can extract energy by breaking it down in two processes, one aerobic or two in terms of fermentation. Okay? One is better than the other. Glycolysis is the pathway, the first pathway that most people learn in metabolism to extract energy. So, all of the energy at the beginning is represented in the glucose itself, the bonds of glucose. So all the potential energy, all the delta H, the bond energies, right? And we're going to convert that into energy through the process. Now, glycolysis is 10 reactions. They're usually defined into the first 5 and the last 5. The first 5 are really called the prep stage. The last 5 is the payoff stage, in which what we're really wanting to do is make energy, and a lot of people, they think energy is only ATP. So the first thing that we do to make energy is what? We use energy. And then the third step, we use more energy. If you need energy, why are you using it to get it? Well, you know the old saying, to make money you have to. That's right. And so we are going to have to spend a little money to make a little money. And so we will use some energy molecules, and in the prep stage we are investing energy to get to the molecules in the right shape so that we can extract. And by the payoff, we start getting double reactions, and we'll start paying off, and we will, in this step, produce 2 ATPs, right? At this point in time, we're net zero. Invest 2, take out 2, and at the end, we're going to make 2. Okay? Now, along the way, I want you to recognize where the pools of energy are. At the beginning, all the energy is in glucose. All right? Once we get to pyruvate, there's a lot of different places it can go. Pyruvate can go to ethanol, it can go to lactate, it can go all the way down to CO2 and water, and there's a whole lot of other fates that can happen. Okay? The aerobic oxidation of glucose creates CO2 and water. It is one of the first reactions you learn in general chemistry. Combustion of a hydrocarbon makes CO2 and water. Okay? Gives off lots of heat, gives off lots of energy. But we're going to do it in a way that the energy is not given off as heat, but is converted into another form. Okay? The thermodynamics of all of this, and you need to know the overall reaction, all right, will produce 2 pyruvates, 2 NADs, 2 protons, 2 ATPs, and 2 waters. All right? And the glucose, and if we actually add up Hess's law, we will get out of this a net 85 kilojoules per mole. How much energy are we extracting from glucose using glycolysis? If we get out 85, how much are you supposed to get out? 2,840. Did we get a lot of energy out of this? Not at all. But we did set it up in such a way that we're going to extract that. We've set it up so that we can get the energy. Glycolysis doesn't actually extract a lot of energy, but it allows us to treat it and get it ready. All right. Go ahead and review those organic videos, the organic reaction videos. That would be to your benefit, all right, for next time. We will then start looking at, got a couple more slides till we actually start doing the glycolysis and breaking it down and going through that, all right?